Hello again. This is a follow-up video on one that we just made. It was from a set of sites from this book, Hawaii By Sextant, where we had a series. I did it the last video, and there'll be links back and forth between these. The last video just showed how to do a site reduction of Moon and a site reduction of Venus using the StarPilot in the iOS version. The technique's essentially the same for the iOS, for the PC version, for the TI calculator version. And so the issue that we want to focus on here is a special unique feature of the StarPilot, a feature that in fact was pointed out and recognized by the latest edition of Bowditch as a unique tool in celestial navigation. It's a way to optimize the sites and figure out which of a set of sites is the best one. And in this case, we have these are the sites we did that we did in the voyage. There were 3 sites of Venus and 6 sites of the Moon. And the example in the last video just randomly did this one and I think this one. Just took those 2 and did those as a site reduction, and then they're plotted manually and then plotted in the calculator. The calculator, this StarPilot program can also plot the sites. And so what I want to do now is show the function called Site Analyzer, or we call it, and in our textbook, in our celestial navigation textbook, we call it the Fit Slope Method, the Fit Slope Method, and that's what Bowditch refers to it as well. And so I want to illustrate that. It is discussed in some detail in the back of this book in the analysis section. This is a way to automatically advance lines of position. These are some real data, actually, the logbook, a page of the logbook from the actual voyage where this methods was done by hand. And then here comes the Fit Slope Method, and it's for cases where you have limited data, or like here's a case where it looks like we're trying to squeeze a fix out of 2 sets of sites from Venus and the Sun. It looks like where there's a narrow angle of intersection, and when you have limited data, you want to just do your best type of analysis to get the best data. And this method is explained there, and I can just tell you quickly what it does is we have the measured data, and normally you would just fit a line through there to find the best line that measures the progress of these sites and see how the sites, your measured sites, correspond to that line over a short period of time. They go up in a straight line. But the technique that we're taking advantage of is when we fit that line, when we fit that slope, when we fit that line, we actually don't have so many degrees of freedom because we know the slope. In other words, we can go and calculate at some random time during the beginning of our site session, like this one, and some random time towards the end of the site session here, we can just calculate what the calculated height ought to be for that. And I don't care that it's not going to be right. We don't have the sextant corrections or anything like that. That doesn't matter. We just get the HC at some time here and the HC sometime here, and then we plot those 2. And this you can do graphically. You can do it with paper and pencil just as well, if not better maybe, than you do with a calculator. And then once you know this slope, this is the way that line has to go. So then when you're fitting your data, you don't just randomly lay your ruler on the normal guideline is you put your ruler on the page, try to go through as many points as you can to fit the line, and then leaving maybe as many above it as below it, and then just ignoring ones that are a long way off of anything else. So fit as many as you can, same up and same down, and throw away odd ones, wanderers. But in this case, we know more than that. We know the slope of the line, so we don't rotate that line. We just bring the line up at the fixed slope and then fit it, and then we can see what's going on. And sometimes if you have 3 sites, one will be way off the line. It'll be way off the right slope, and the other 2 will be on it, and then you can just choose it and then average those two that are on the line, and you got the best site. So anyway, that's described in that book. Oh, here's actually an example of that. Here's 3 sites, those 3 Venus sites. And there's the slope. We know the slope. We calculate the slope. And then this is zoomed in. And you'll see with a calculator, even with a calculator, you got to zoom way in if these sites are very far apart in time. And you see these two are sort of right on the slope. These are V1 and V2. But V3, and I forget now which one here is the right. Oh, it must be that the black one is the data and the white one is a computation. So it looks like that this one is off. This is off. So your best fix is going to be to ignore site number 2 and then just average these two, or literally take either one of them, or just take a point on the line in between them. So in other words, disregard that site and take one of these, either one of these. In other words, either one of these, 1 or 3, is the same as mathematically averaging all 3. We only learned that this one or this one is equally good by taking all of them. And so then the back of the book goes through some of the cases and applies that. And now we're just going to see how you can do that with the calculator and the sites that these sites that we have in hand here. And so let's look, and I've typed all the stuff in so we can just look at it. So I'm trying to coordinate right hand here and the left hand on the mouse. So, and then there's the not that very exciting screen, but this is the first screen. And this is what you would do here is, if you're doing that, you would be entering all these sites in a site reduction mode. So you go up here to site reduction, and then or actually, let me just see, since I loaded, it looks like it's starting from scratch on site 7. So let me go back, go back with a finger on the right machine, and I'm going to go to Celestial Fix and then Review Sites. Now I can show the sites one by one that I typed in here. And this is just the first one, 1329.35, with a height of 5238.9. So that's the first one. And then here's the result of that site reduction. And then refer back to the other video to see how these numbers went in. Then you can just step through these. That's the next one, and the next one, and the next one. And that's those 6 sites. So you've entered those, and it turns out it's very fast to do this, because once you've entered in the lat, lon, the IC, and the date and time, and the date and everything, and you do one of them, then when you do the next, you say next site, then all you have to do is change this number and this number. So you actually can add these all in. It's just a very nice layout for getting all that data in at once. And then you do a fix, or you do what we're going to do now, and just we're trying to collapse all of these into basically one site. In other words, I want to take advantage of the fact that I have 6 sites, but I want to statistically know what is the best one that's representing all of them in the best way, and then use that one. And I can keep that one and throw the others away and just plot that one. Okay, so that's what we do. So now I'm hitting back here, and then I'm going to, where is this? I may have to go back again, back again. Now maybe let me go to Celestial Bodies, Site Analyzer right here, Site Analyzer. Okay, so then it shows you the sites that are in the active set. Those are right here. And then you have to put in your DR position, because we're going to use that DR position in this thing to actually calculate the theoretical height of each one of these in order to fit the slope. Well, this would calculate the whole curve, actually. And then you have to know, and it's very important, you have to know your course and speed, because when this calculation's done, at each one of these times, it advances the boat's position and calculates the slope again. So that's a subtle, important point of the whole process. So now you can just hit Analyze here, Analyze, and now let me just see how this works. Okay, and now again, you just have to, one of these, let me pause. I'm going to pause the video. I left my pointer. You can do this with your finger, obviously, but they make since we're homing right in on this thing, it's a little nicer to have one of those kind capacitive pointers. There's $5 or $6 each, and then you just can touch these screens a lot better. Let me pause for just a minute. Okay, I'm back, and I have this pointer. I hope it's a little bit better. Let me just see. I can drag this up and down a little bit. Yeah. Okay, let me see how this... Oh, I've got to also get a different... Okay, that's better. All right, so I can do that. So what we see here, these are the moon sites, and the first thing we're seeing, it's all pretty good data. It's all pretty good data. These things line up. There's no flyers or no obvious blunders or something like that. But it does look like that these 4 sites up here and these 2 sites here are in a different set. In other words, these actually agree. They both agree with the right slope. See, if I bring this up a little bit, there, you see these agree here pretty well, and they're off just a little bit. And that's, I can tell you that the distance between these two here, let's see, if I zoom this, let me just see to what extent I can zoom it with my fingers. It's a pinch zoom situation. Now, once that's zoomed like that, then you read up here the miles, like that's 5240.9. So if you want to see what miles that is here or down here, let me move that up a little bit. Okay. So if I touch this here, right about there, you see I've got 52.1 miles, and here I have 59, 52. So that's about 7 miles there. So let me bring this back down. So that's fitting right there. So that's actually within, these are pretty good, but it looks like there's 2 basic sets of data, and this set of data and this set of data disagree with each other by about, looks like almost a mile or 2 miles. And so in a sense, now if I brought this one, if I look just at this set up here, and I can bring this down to look at that, and if I look at that set here, these are all really about the same. This one may be not quite as good as the other two, but in other words, what we've learned here is that it's probably better to average these 4. These were the first 2 taken, maybe of the moon, and I don't know, what the horizon looked like then. Is this morning or evening? This is 6 o'clock in the morning, and it's getting brighter. So it could be it's just the horizon's getting a little sharper. I would tend to average these 4, but it doesn't matter which one, and you could literally just take a line right off of here. You could just literally tap that if you wanted to and use that for your site. It doesn't matter. So of these, you could average, well, you can't, be careful, you can't average these 4 right here unless you did the advancement. This picture is not advanced here. So what you would say is any one of these are just as good, or you would go back to the back of the book and apply this kind of, do this automatic advancement of every one of those and then average them, and that would give you the very best one. But the main thing we're looking at here is for big effects. These are all data, within a mile or two, these guys. And what do we actually see in the answers? Let's look at the answers. And we're looking at the last, look at that. We see this too. Look at this. This has A values. That's 1.7 and 2.4, right? So that's an average of, about 2. And and these 4, these are all a little bit better, right? The A value is a little bit, they're more consistent. I don't know. So it looks like these, any one of these would do the job. It turns out we chose this one. It's probably just as good as any. All right. So that's that. So it turns out that just looking at, I took these sites I did the analysis of these simply because we had done the demo on how to do a site reduction of these 2 for another purpose, a request of request that others be done. And this shows that just randomly looking at things, we don't find particularly interesting examples. But in this case, both these sites were all pretty good. But this technique will indeed point out when you get bad sites, and if you have to, it'll help improve sites with poor data. And so I'll leave it at that.